Okay, welcome. Period 9, the internet, everyone, everywhere. We are going to do what is called a Turing reduction. We started this problem in class, but we didn't finish. So I thought I would sort of do it all over again really quickly. Hopefully this can take only like 10 minutes. What we talked about in class was that there's this general problem called the word problem. And the word problem says, give me a finite alphabet of characters, give me a bunch of rules which enable me to substitute certain substrings from a given string with certain other substrings, and just consider all possible strings that you can create by following any finite sequence of these string substitution rules. And what we would like to know is whether a certain string is derivable from another string given a certain sequence of rules. Okay, and so I'm going to suppose that the word problem is solvable. And quite shockingly, we will find that this leads to a contradiction. And so actually we cannot solve the word problem, not in general. Some special cases might be solved, but in general not. Because to be able to solve the general word problem means that there must be some kind of algorithm which always works and always terminates no matter what word problem we're being asked to solve. So as I was just saying, given any finite alphabet, you give me some character set, and I have a finite list of substring replacement rules. So little rules which tell you to replace one substring with another substring within some larger string. We now have given ourselves the power, this is a proof by contradiction, to determine whether a given string is derivable from another given string. And so I formalized this. I didn't do this in class, it's not really formal, I just wrote it out more clearly. What we are supposing we have is this word problem algorithm takes a certain alphabet, it takes a certain list of rules, it takes a start string, and it takes an end string, and it answers the question, can I or can I not start with the start string and end with the end string by following a finite sequence of substitutions from the list of substitution rules. Okay, and this is called a halting reduction because what we do is we show that if, on the assumption that the word problem is solvable, we can solve the halting problem. And we can solve the halting problem, we proved that already. Okay, and I'm going to prove to you that if I had this power to solve arbitrary word problems, then I could solve the halting problem. And this is what we did in class, basically. We said, okay, take, what is the halting problem? The halting problem is the problem of being given the Gödel number of some Turing machine and some input, and we answer the question whether or not the Turing machine coded by M halts on input n. So let's suppose we have that, a little m and a little n. Little m is the Gödel number for Turing machine big M. Okay, how can we solve the halting problem? Well, we're going to decode this number m into the Turing machine. So we've done that already. And this Turing machine is going to have some finite number of states. Suppose it has p states. And let's label them q1, q2, q3, all the way up to p. Okay, well now I am going to show you how we can solve the halting problem by turning it into a word problem. Okay, for my characters, I'm going to use 0 and 1, which are characters on the tape of my Turing machine as it processes some kind of input. I'm going to take a symbol for every one of the states. So if I've taken an arbitrary Turing machine M and it has p states, then I have adding p symbols to my alphabet. Then I have this special character H. You'll see in a minute what it does. Basically, it just marks the left and right endpoint of my tape. Now, Turing machines, in fact, have an infinite tape, and the full power of Turing machines require that that tape be infinite. If that tape is like finite in some kind of way, then there are certain problems that sort of can't be solved. And I think you actually can solve the halting problem for Turing machines with a finite memory. But anyway, our machine is infinite, so it's kind of weird to say the left end and the right end of the tape, but as we've seen in class, in any particular computation, you're only going to use a finite amount of the tape. And so you can think of H as marking the left edge and the right edge of the tape that we've sort of traversed so far. And then to the left of that and to the right of that are just an infinite string of blanks or zeros. Okay, what is, so that's the alphabet. What are the rules? Well, to get the rules, what we're going to do is we're going to take the Turing machine and we're going to systematically go through that Turing machine. It has a finite number of states. It has 2 rules for every state. What to do when you read a 0 and what to do when you read a 1. So if there are p states, then there are, the last state is the halt state. It never has any rules coming out of it. So if there are p states, then the pth one is the halt state. So there are probably like p minus 1 like real states. So there are 2 times p minus 1 rules. Certainly a finite number of them. And for each of those rules, I am going to sort of massage them into really being string replacement rules. Okay, so what does every Turing machine rule basically tell you to do? Every Turing machine rule says, yo, look at the tape, based on what state you're in, based on whether there's a 0 or a 1 on the tape, you're either going to write on the tape or move left or right, and then transition to a new state. Okay, and so an example of a particular configuration that our Turing machine might be in, this is just an example, perhaps our tape looks like this, 1, 1, 0, 1, 1. And then by default we have an infinite amount of zeros to the left and to the right. And perhaps our cursor is on this 1 right here, and perhaps we're in state Q4. Well, for our purposes, we are going to express that as follows. We have a symbol, the Q4 symbol, and so we're going to insert that here. And we are, by convention, if our cursor is on this 1, we're going to place the Q4 just before that 1. So when you see Q4 1, we interpret this as meaning we're in state Q4 and our cursor is on the character just after that symbol. And then these H's are just these little kind of parentheses or something which say that this is the only tape that we've explored so far. Everything to the left of H is an infinite number of zeros. Everything to the right of H is also an infinite number of zeros. So what I've now done is I've captured with a finite string not just what's on the tape, but also where the cursor is and also what state I'm in. Okay, let's do an example to see how this works. Here I have a Turing machine. I just took a pretty simple Turing machine with 2 real states and a halt state. So if I'm in state Q1, I read a 0, I write a 1, and I go back to state Q1. If I'm in state Q1, I read a 1, I move left and I go to state Q2. If I'm in state Q2 and I read a 0, I write a 1 and I go back to state Q2. If I'm in state Q2 and I read a 1, I move right and I go to the, it would just be Q3, but I'm going to write it as QP because it's the P state, the final state, the halt state, for which there are no directions. Okay, and so this machine has 4 rules. And so let's take the first one. Let's take this rule, which we can write according to the other convention that we had from the other day. We can write this as Q1, 0, 1, Q1. It's the rule that says if I'm in Q1 and I read a 0, write a 1 and go back to Q1. Okay, so just move this camera for a second. Yeah, perfect. Okay, well, think about what it means to follow this rule. What it means to follow this rule is that I'm in Q1, my cursor is on a particular 0, and what I should do is replace that 0 with a 1 and go back to Q1. So, for example, perhaps our tape looks like this. Left edge of the tape, 1, 1, 0, Q1, 0, 1, 1, H. Remember, this means our cursor is on a 0, this 0, and I'm in state Q1. Well, following this rule means if I'm in Q1 and my cursor is on a 0, I'm supposed to replace that with a 1 and go back to Q1. And so, what I should do to update this, by following this rule, I stay in state Q1, my cursor doesn't move, but that 0 becomes a 1. Okay, so this, what just happened was I replaced the substring Q10 with the substring Q11. And that substring replacement rule in fact encapsulates the idea that if you're in state Q1 and your cursor is on a 0, then keep your cursor in the same place and replace that 0 with a 1. Okay, and so in fact, it's not just this rule, so what I'm proposing sort of in general is the following substring replacement rule that says, so here are my rules. It says anytime you see a Q10, replace it with a Q11. And it seems like that's totally sufficient, but there is kind of like a technical issue, which is that, remember, this H is really a placeholder for there being an infinite number of zeros. And so if anytime Q1 is right up against an H, it also means that the cursor is on a 0. And so the other little rule I need is Q1H goes to Q11H. And that rule will account for the example in which I have like H1101 Q1H, as I was just saying. I can faithfully follow that first rule by writing it as H1101 Q1. That H is really, there's a 0 there, so 1 and now H. So that's how my string kind of gets longer, but I keep putting that H there on the edge just to kind of keep things under control. So in this case, I replaced these 2 characters with those 3 characters. Okay, I have 2 rules so far. I'll just put a blue, no, I used blue already. I'll put a purple box around, around these 2 rules, and now I just kind of do the same thing for my other 3 transitions. So consider the state Q21 LQ2. Okay, this is a little tricky. This says if I think this should be Q1, yeah. Consider the situation in which I'm in state Q1 and I read a 1, I'm supposed to move left and go to state Q2. Well, think about what that means. It means that my cursor is on a 1 and I'm supposed to move left. But if I'm supposed to move left, then now I am moving to the left of whatever was on my tape. Well, there are multiple things that could be on my tape. There could either be a 0, so if it's 0 Q1 1, yeah, then that means there happens to be 0 to the left of me, but my cursor is on a 1 and I'm in state Q1. What am I supposed to do? I'm supposed to move left and go to state Q2. So I should move left, and now I'm in state Q2, and I am, this Q2 is to the left of 0, because that's indicating the fact that I'm now have my cursor on the 0 that was initially to the left of me. That's what it means to move left. Boom! That's one rule. What's another rule? Well, the exact analogous one. Q1, 1 should go to Q2, 1, 1. In other words, if I'm in state Q1 and my cursor is on a 1, but there happens to be a 1 to the left of me, I'm supposed to move left. So when I move left, now I'm in state Q2 and my cursor is on the 1 that was to the left of me. Okay, and then there's one more technicality, which is anytime I'm moving left, I have to worry about being possibly at the edge of the tape. So if it's HQ1, 1, then I need to, that means there was really a bunch of zeros to the left of me, so I should replace that with HQ2, 0, 1. Yeah. Okay, I claim that these 3 rules, and I'll put a purple box around it, completely capture this second rule here, this one that tells me what to do when I'm in state Q1 and I read a 1. Okay, and now I just finish it off. These 2 are basically the same. This one is just exactly like the previous one, right? So we're going to have 2 rules. The one that says I'm in Q2 and I read a 0. Then I'm supposed to just stay in Q2, but it's a 1 now. And then the one that accounts for the fact that I might be at the right edge of the tape. So Q2, oh, that's interesting. Well, whatever. Q2, H, and should go to Q2, 1, H. because that also counts as reading a 0. And now I push the edge of my thing out a little bit more. Okay, one more. So put a purple box around this. Now consider Q21RQP. This is very similar to this one. This is getting a little kind of technical and maybe kind of repetitive. But either, now if I'm moving right, I need to consider what was to the right of me. So if I have Q21 0, I should go to 1 Q2 0. In other words, if I'm in state Q2 and I read a 1 and there happened to be a and my cursor's on the 1 and there happened to be a 0 on the other side of that 1, then I'm supposed to move right and go to, no, I'm supposed to go to QP here. This is systematically wrong on my paper. Okay, QP. I'm supposed to go to QP after moving right. Now my cursor will be on the 0 that was to the right of me. If it happened to be a 1 to the right of me, but my cursor was on a 1, well, following that rule, I'm supposed to move right. So now that 1 that I was reading will be to the left of me, and now I'm in state QP, but my cursor is on the 1 that was to the right of me. And then finally, there's still a little twist about what to do when I'm on the right edge of my tape. So if it's Q21H is the other option, then I'm supposed to I'm reading a 1, I should move right, so that's going to be 1 QP, and that H is really like a 0H. Okay, we are basically done now. I have translated this Turing machine, or I've translated the transition rules of this Turing machine into a bunch of substring replacement rules. And here comes the brilliant move. The brilliant move says, dude, the way we've set up our Turing machines, such that there's only one halt state. Anytime the machine halts, we include a direction for it to be sent to the halt state. And in the halt state, you never leave, nothing ever happens. What that means is, anytime I'm asking a particular Turing machine on a particular input, whether or not it halts, I might as well be just asking, does this machine, under any circumstances, does this machine enter the halt state? So the question of does the machine M halt on input N is equivalent to the question, does the machine M on input N enter the halt state? And based on our representation of the Turing configurations as strings, that might as well be the question, does the symbol QP, the symbol for the halt state, ever appear as one of my strings? If I am following some sequence of string replacement rules, following, and ever the symbol QP appears on one of my strings, then immediately that string must represent a Turing configuration in which I'm in the halt state. And regardless of what else is on that long string, some sequence of 1s and 0s, I don't particularly care actually what data is on the tape, I just care whether the machine halts. And so the machine halts if this character QP exists anywhere on the string which represents the Turing configuration of the Turing machine on that input. And so I am now going to add, so I'll just write that really quick, right? If the symbol QP ever appears in the sequence of what have I even called these things? In the sequence of, I'll just say in the sequence of strings, because remember this system is replacing a string with another string with another string with another string with another string. In that sequence of strings, if QP ever appears in any of the strings in that sequence, then the machine halts. Okay, so now I just clean it up. I clean it up by throwing in a couple of extra rules. The one that says QP0 should be replaced with QP, 0 QP should be replaced with QP, the rule that 1 QP should be replaced with QP, and QP1 should be replaced with QP. I possibly don't need all 4 of these, but I think I do. I'm not really sure. Anyway, I'm going to put a purple box around these because these are 4 more rules I'm adding to my system. And what these do, in some brilliant kind of way, is they just clear up the whole string, right? I might have the symbol QP appearing in some very long string with lots of zeros and ones and all that kind of stuff. But these 4 rules just shrink and shrivel that whole thing up. And basically, what remains when we're all done is the simple string HQPH. In other words, if the machine halts, then there must be some sequence of these rules that you follow, which leads you to a string that has a QP on it, which can lead you, by following these rules, to this string. So this is the string whose existence as the end product of the sequence of substitutions indicates that the machine halts. And if this string appears in the sequence of string substitutions, then the machine will halt. And if the machine halts, there is some sequence in which this appears. Okay, and so if I've given myself the power to solve the word problem, then I can use this power, this word problem, to create a particular alphabet. The alphabet is 0, 1, H, and like 1 symbol for every state in the Turing machine. This gamma, and gamma is simply, for our particular machine, gamma is just all the rules in the purple boxes. I'll just leave it at that. And then, what string do I want to start the word problem up with? Well, I'll start it up with a blank tape. Or not a blank tape, a tape with N on it. So it's going to be H, 1, 1, all the way, a whole crap load of ones, N of them in particular. And the whole question of does this machine M halt on input little n is equivalent to do I ever get the string HQPH from the string H11111111H. If I can get from here to here, then that means that machine M halts on input n. Okay, but this means I can solve the halting problem, but I can't solve the halting problem, so that's a contradiction. And so I can't solve the word problem either. All right. Thank you. See you in class.